Whether a film is being used to take a simple holiday snapshot or being used by the BBC cameraman to shoot this program, the overall photographic process remains the same. The patterns of light and shade are captured by millions of tiny crystals of silver halide. Color photography is only 50 years old. But the black and white process was developed about 150 years ago. It was in the early 1800s that the idea of recording permanently the images focused by a lens began to become a reality. The first man to succeed in capturing an image was a Frenchman called Niepce. This photograph was taken in 1829 and would have needed several hours exposure. However, this process didn't involve silver at all, but white bitumen spread on pewter. Niepce's ideas were developed by a fellow Frenchman, Louis Daguerre. He used silver-plated copper, sensitized with iodine vapor. This is one of his first pictures. An exposure of around half an hour would have been needed. Daguerre's process was announced publicly in 1839 and received tremendous acclaim. Everyone wanted their picture taken. But in the same year, a different process was announced. It pushed the daguerreotype into the history books and earned the inventor a reputation as the father of photography. He was an Englishman, and his name was William Henry Fox Talbot. Using paper impregnated with silver chloride, Fox Talbot's method produced a negative from which positive pictures could then be made. This is his first picture. It shows a latticed window taken at the family home at Laycock Abbey. Pictures like these would have had exposures as short as 30 seconds, and the same chemical principles are still used to this day. But what is it about silver halides that makes them so eminently suitable for photography? In a word, sensitivity. Looking at an undeveloped negative under the electron microscope, we can see the crystals of silver halide. Each crystal consists of a lattice of silver ions, shown as red, and halide ions, shown as blue. Light causes electrons to be released from the halide ions, and if a silver ion combines with one of these mobile electrons, a silver atom is formed. Small clusters of silver atoms are produced, forming what's known as the latent image, and these clusters act as centers for the millionfold amplification that occurs during development. This crystal of silver halide has been exposed to light. During development, further silver ions are converted into metallic silver around the original tiny clusters of silver atoms. It is this amplification that makes the silver process so exceptionally sensitive. But this does mean that the resolution of a photograph is limited by the size of the silver crystals or grains. We're not usually aware of them when we look at a picture, but as we get closer, the grains become more obvious. So far, our picture is only in black and white. How are we to record color? A color picture can be broken down into 3 monochrome separations. We can project these separately. When we combine them, the original picture. And all color film works on a similar principle. This section, through a color negative, shows the 3 separate layers. Each contains just one color. But how does this happen? Silver halide crystals are normally most sensitive to blue light. This is the top layer. A yellow filter prevents any blue light reaching the layers underneath. The next layer has been sensitized so that it responds to slightly longer wavelengths and records green light. The third layer responds to even longer wavelengths and records the red light. Development of this latent image produces silver grains. Around the grains, dyes are formed by reaction of the developer with different compounds present in each layer. After development, the remaining silver is dissolved away. But remember, this is a negative, so the colors are the subtractive primaries. The varying density of the yellow layer controls the blue transmission of the negative. The magenta controls the green, and the cyan, the red. When the negative is printed, the colors are reversed, and a positive record is produced. Silver processes are exceptional because of the high sensitivity of the film to light. Even on a dull day like this, one can take a color photograph in 1/100th of a second. But the silver process has two disadvantages: the expense and the time it takes to develop the picture. So what other photoreactions can we use to produce images? One of the commonest is this process, which is used to make copies of documents. This simple demonstration illustrates the principle. A cardboard cutout is placed on top of a piece of paper impregnated with an aromatic diazonium salt and exposed to ultraviolet light. Ammonia vapor is used as the developer. The diazo system is very insensitive. You couldn't use it in a camera to take a snapshot, but it has the advantage of being cheap, as it doesn't use silver. The areas which weren't exposed to ultraviolet light slowly darken. Let's look at the chemistry involved. In the area exposed to ultraviolet light, the diazonium salt dissociates and nitrogen is released. In the areas not exposed to light, the diazonium compound is free to react with a color coupler which is present in the paper. This reaction needs ammonia and leads to the formation of an azo dye. A drawback is that both the silver and the diazo systems require a separate exposure for each copy. What can we do if we need a very large number of copies? Images formed by photopolymers can help us here. They've found a number of important applications in printing. In this case, the original is a silver negative. The blue sheet underneath the negative contains a polymer which undergoes cross-linking when exposed to ultraviolet light. So the areas that are exposed become hardened. Once exposure is complete, the unhardened areas are dissolved away using an organic solvent. This image can now be used to generate a large number of copies, because printing ink will only adhere to the areas of hardened polymer and not to the area in between. The advantages of offset lithography, as it's called, are that the plates are cheap and simple to prepare. It's called offset because the plate itself doesn't come in contact with the paper. Ink is transferred from the plate to the surface of a large rubber roller, and from here to the paper. This ensures a perfect contact. If color separations are made from an original and each made into a separate plate, then by changing the ink color and running the paper through the machine several times, the full color picture can be built up. The first color run is yellow, the second cyan. When magenta is added, we have what looks like the complete color picture, but to get a full depth of color, black is added. But wouldn't it be nice if we could do away with the need to process the image? Much of our research here at Aberystwyth is concerned with a special class of compounds which show a reversible color change on irradiation. Such compounds are called photochromic. At the turn of the century, a German chemist called Hans Dobbe first synthesized the type of photochromic compounds with which we work. He named these compounds fulgides. This simple experiment reconstructs a discovery that Dobbe made regarding a rather unusual property possessed by some of the compounds he had synthesized. It's shown best by first dissolving the bright yellow crystals in an organic solvent to make a dilute solution. A white filter paper is soaked in this solution and then dried. When this filter paper is exposed to ultraviolet light, it causes the fulgide to change color. Dobbe demonstrated the potential for image formation, and we can show this in this simple experiment by irradiating the sample with an ultraviolet lamp and using a glass negative to produce the image. But Dobbe would have found that he couldn't keep his image, that it faded. And what's more, when he tried to carry out the photochromic reaction a number of times, he would have found that the material wouldn't color anymore. It had fatigued. Conversion of A into the colored form B is caused by wavelength A, often ultraviolet. Reversal can be caused by a different wavelength B, usually visible light, or by heat, which can also convert B back into A even in the dark. Irradiation may also convert B into compound C. This is an irreversible photochemical reaction that causes fatigue. Dobbe implied in his publications that the photochromic response was due to cis-trans isomerization that occurred in the crystals. But in this, he was wrong. The color change occurs just as well in solution. And what's more, fulgides, which cannot show cis-trans isomerization, also have photochromic properties. Using modern techniques to study the fatigue products, we have been able to discover what happens in the photochromic change. The reaction centers around this trine. For clarity, we'll write it in this form. In 1968, our research confirmed that the photochromic reaction involved a reversible electrocyclic ring closure. But one problem with this molecule is that when it's in the uncyclized form, there are a large number of conformations. For cyclization to take place, the molecule must be in this orientation and not in an orientation like this. So the first thing we can do in order to make a useful photochromic compound is to make this molecule more rigid by adding this anhydride ring. You can see that the molecule is locked in a partly fixed orientation. Of the 3 double bonds, only one now is free to move. But when this cyclizes, the cyclized form still only absorbs in the ultraviolet region, so there will be no color change between the ring closed and the ring opened forms. So we must now add a chromophoric group to the molecule. The effect of the changes which we have carried out are twofold. We have introduced a grouping which imparts color into the cyclized form. 4 double bonds ending in a carbonyl group. And the color imparted by this chromophoric group is enhanced by the two methoxy groupings which we have also introduced. Let's now look more closely at the photochromic properties of this type of compound. This is the absorption spectrum of the ring-opened, the uncolored form. As expected, there's a large absorption over in the ultraviolet. Let's convert the compound to the colored form. The sample is irradiated with ultraviolet light. This particular full guide turns red. If we now run the full absorption spectrum of the colored form, shown by the red line, we can compare it with the uncolored form. And we can see that there is a loss of absorption in the ultraviolet region, and a strong absorption has appeared in the visible region. And it's this absorption, of course, which causes the color in the ring-closed form. This photochromic system is still not suitable for most commercial applications. Firstly, because it thermally fades, and secondly, because it fatigues by the migration of this hydrogen. Photochemical fatigue involves reactions like a 1,3 hydrogen shift. The formation of this product is irreversible and means that the photochromic compound is gradually destroyed. We can prevent this by replacing the migrating hydrogen atom with a methyl group. This methyl group doesn't migrate, and the problem of fatigue is solved. And so, incidentally, is the problem of thermal fading. So what we've done, by careful molecular tailoring, is we've designed a fatigue-resistant, highly fatigue-resistant photochromic full guide. The compound can be colored and erased thousands of times without any detectable fatigue. But in addition, because we have prevented the thermal fade, the image which we can produce can be stored indefinitely in the dark. Have you considered the problems of map makers trying to keep maps up to date? New motorways being built, old buildings being demolished. It would be very handy if this information could be stored in a computer. The British company LaserScan have developed a machine that is already being used by the Ordnance Survey. And interestingly enough, this system finds uses for 3 of the different ways of image recording which we have used so far. This is the computer where the information is stored. But how does a map actually get into the computer in the first place? Consider this problem: to update the plan of the buildings here at the Open University. The first step involves a traditional type of image. We copy the existing plan onto a silver negative, about the size of a postcard. We use a silver image at this point for the traditional reason: its very great sensitivity. The silver negative is placed inside the machine, which is called Fast Track. What this does is to scan the negative using a laser beam. The positions of the lines are recorded and stored in the computer. By projecting the negative onto a screen, the operator can see what is happening. Here is the science faculty building being scanned. Once the plan is stored in the computer, the instant imaging of photochromic material comes into its own. Rather than referring to the original map, we can get the computer to draw it out again on a blank piece of photochromic film. We're now ready to update the map. A construction of a new group of buildings is already underway, and this information can now be added to the photochromic film. So there's the new map, including the extension. Once we're happy with what's on the screen, the computer stores the new information. But supposing we want a permanent copy of the map. Inside the machine, a mirror moves out of the way, and the computer uses the laser to draw the new map on a piece of diazo film. We use diazo film at this stage because of its very low sensitivity, which means that we can handle it in daylight before processing. From the diazo film, which looks very like a silver negative, we can make a diazo enlargement. There's the new map, and there's the extension. Of all the imaging processes that we have seen, we cannot favor one over another. In their properties, they complement each other rather than compete. The conventional photography requires high sensitivity to light, which will depend on silver for the foreseeable future. Diazo copying is inexpensive and will be used for the cheap copying of documents. And photochromic compounds will find applications in optical information storage, in video recording, in security printing, and even in sunglasses, where fast coloring and rapid thermal fade are required.